go ahead and get going here. Today we're going to be talking about the logic of quantified statements. If the screen will cooperate with me today, apparently not. What is wrong with the screen? All right, predicates and quantified statements, part 1. All right, start off with a definition. A predicate is a sentence that contains a finite number of variables and becomes a statement when specific values are substituted for the variables. The domain of a predicate variable is the set of all values that may be substituted in place of the variable. So let P of x be the predicate x squared is greater than x. With the domain, the set R of all real numbers, which of these statements here are true and which are false? P of 2 would be x squared is greater than x, so 4 is greater than 2. That would be true. 1/2 squared is greater than x, 1/2. That's not true because x squared is a quarter. And it's hard to read, but x squared being minus 1/2 squared, which would be 1/4, is greater than minus 1/2, so that would be true. It would be true, false, and true. And they go through the math of showing that these are true or false. Okay, another definition. If P of x is a predicate and has domain D, the truth set of P of x is the set of all elements of D that make P of x true when they are substituted for x. The truth set of P of x is denoted by the symbols you see there on the screen. X is an element of D such that P of x is true. I believe the vertical bar is the equivalent to saying such that. Let Q of n be a predicate, be the predicate n is a factor of 8. Find the truth set of Q of n if the domain of n is positive integers or the domain of n is all integers. The truth set for all positive integers would be what, 1, 2, 4, and 8. And if n is the set of all integers, it would be that plus minus 1, minus 2, minus 4, and minus 8. Right? So there you go. The universal quantifier, the inverted A. One sure way to change a predicate into a statement, is to assign specific values to their variables. For example, if x represents the number 35, the sentence x is evenly divisible by 5 is a true statement. Another way to obtain statements from predicates is to add quantifiers. Quantifiers are words that refer to quantities such as some or all, and tell how many elements a given predicate is true. The symbol inverted A is called the universal quantifier. Depending on the context, it is read as for every or for each, for any, given all, or for all. For example, another way to express the sentence, every human being is mortal, or all human beings are mortal, is to write inverted A, human beings X, comma, X is mortal, which would read, for every human being X, X is mortal. So if you let H be the set of all human beings, then you could write symbolically the statement more formally as, for all X that is an element of H, X is mortal. Another definition, that Q of X be a predicate and D the domain of X. A universal statement is a statement of the form given. It is defined to be true if and only if Q of X is true for each individual X in D. It is defined to be false if and only if Q of X is false for at least one Q of X, or Q in D. I'm sorry, X in D. A value for X for which Q of X is false is called a counterexample to the universal statement, which would make it the statement false. Let D equal 1, 2, 3, and 5, 4 and 5. Consider the statement X squared is greater than or equal to X. Show that it is true. You do the math and show for every element in the set you can indicate that that the statement is true. Consider the statement here as being false. To make it false, all you have to do is find a single example where it is false instead of being true. A counterexample to this, where X squared is not greater than or equal to X, would be X being equal to 1/2, for example. That would be a counterexample showing that this statement is in fact false. So you show that they're all true to make the statement true, and then for showing it to be false, you find a counterexample. So the other quantifier is the existential quantifier, the inverted E. This symbol denotes that there exists in the statement, in the sentence, and is called the existential quantifier. For example, the sentence, there is a student in Math 140, can be written as, there exists a person P such that P is a student in Math 140. Or more formally, in this form where P is a set of all people. The domain of the predicate variable is generally indicated either between the existential quantifier symbol and the variable name, or immediately following the variable name, the words such that are inserted just before the predicate. So let Q of X be a predicate and D the domain of X. An existential statement is a statement of the form given here. It is defined to be true if and only if Q of X is true for at least one X in D. It is false if and only if Q is false for all X in D. So it's just kind of the opposite of the universal quantifier. Consider the statement. Right, there exists a number m that is an element of the positive integer such that m squared equals m. And you can show that to be true by giving just one example. 1 squared equals 1, so it's true. Let E be the set 5, 6, 7, and 8. Consider the same statement. The statement is false because it's not true for each individual element of E. And you'd have to show that it's false, you would show that each element in the set, this is not true, as we have here. So, A is true and B is false. Formal versus informal language. We've been kind of doing this already to some degree. It is important to be able to translate from formal to informal and from formal to informal to formal to make sense of mathematical concepts that are new to you. And to when you want to think out a complicated problem. So you need to be able to translate between formal and informal forms. Generally, informal forms are done in papers and talking to people, but when writing out a mathematical proof or in some cases writing as well, you use the formal form. So, and this just takes you through translating the formal to informal. For all x in R, x squared is greater than or equal to 0. For all x in R, x squared is not equal to -1. There exists an m that's an element of that's a positive integer such that m squared equals m. So you would rewrite them in this way. All numbers have non-negative squares. Any real number has a non-negative square. The square of each real number is non-negative. There are lots of different ways to express it. All real numbers have squares that do not equal to -1. And there's a positive integer whose square is equal to itself, or one of these other forms. Trailing quantifiers. You do not have to put the quantifier first in an informal expression of the statement. So if 2n is even, you can say 2n is even for any integer n. Just flip the phrases around. For x squared to be less than or equal to 0, there exists at least one real number x. X squared is less than or equal to 0 for some real number x. 2n is even for any integer n. Now, from informal to formal, all triangles have 3 sides. No dogs have wings. Some programs are structured. For all triangles T has 3 sides. For all dogs D does not have wings. And there exists a program P that is structured. Yeah. So just formalizing it. If I'm not mistaken, I said at the beginning or first class of the semester, this is formalizing common sense. Yeah, this is just learning terms to describe the formal way of doing things. Universal conditional statements. A reasonable argument can be made that the most important form of a statement is in mathematics is the universal conditional statement. For all ax, if p of x, then q of x. Remember conditionals from chapter 2. Rewrite the statement informally without quantifiers or variables. For all real numbers, if the number is greater than 2, then x squared is greater than 4. Yeah. If a real number is greater than 2, then its square is greater than 4. The square of all real numbers are greater than 2 are greater than 4. Yeah. Different ways of saying the same thing. Rewrite each of the following statements in the form for all blank, if blank, then blank. For all real numbers, x, for any real number x, if x is an integer, then x is an element of q. For all b, if b is a byte, then b has 8 bits. For all t, if t is a fire truck, then t is not green. There you go. To omit explicit identification of the domain, it is common to omit the explicit identification of the domain and predicate variables in universal conditional statements. I would add if it's obvious. Or it just can't be expressed. There's no notation for the set that is the domain of the predicate. Equivalent forms of universal and existential statements. Observe that the two statements x for all real numbers x, if x is an integer, then x is rational, and for every integer x, x is rational. Mean the same thing because the set of integers is a subset of real numbers. Both have informal translations. All integers are rational. In fact, this form of the statement here can always be written in the form of a of x, for any ax that's an element of D, then q of x, if D is a subset of U. Conversely, a statement of the form here can be written as if x is in D, then then q of x, if the statement is started out in that form. Rewrite the following statements in the two forms. All triangles all squares are rectangles. For all x, if x is a square, then x is a rectangle. For all squares x, x is a rectangle. That sounds about right. For all square x, then x is a rectangle, yeah. If x is a square, then x is a rectangle. Equivalent forms. Okay, we all know what a prime number is. Consider the statement, there's an integer that is both prime and even. Let prime n be n is prime and even n be n is even. Use the notation prime n and even n to rewrite this statement in the two following forms. There exists an n such that prime n and even n. There exists a prime n such that even n. Even number that is prime. Okay. That's what they were looking for. A prime number n such that even n. Yeah. But yeah, the conditional can be written with the and statement. Bound variables and scope. Given the example, consider the following statement. For every integer x, x squared is greater than or equal to 0. And there exists a real number x such that x cubed is 8. Statements 1 and 2 both call the variable x, but the x in statement 1 serves a different function from the x in statement 2. So the x here is bound to this scope, and this x is bound to this scope, right? X is bound by the quantifier that controls it, and that its scope begins with the quantifier and begins with the quantifier that introduces it and ends at the end of the quantified statement. Kind of like a variable that's declared in a for loop is only valid in that for loop because that is its scope. Implicit quantification. Consider the statement. If a number is an integer, then it is a rational number. As shown earlier, this statement is equivalent to a universal statement. However, it does not contain the telltale word all, or every, or any, or each. The only clue is the use of the indefinite article a. This is an example of implicit universal quantification. Existential quantification can also be implicit. The number 24 can be written as a sum of two even integers. Can be expressed formally as this, and the only real indicator of it is the can be. Not it always is, but can be. That is implicitly indicating an existential qualification. So let P of Q and Q of, P of X and Q of X be predicates, and suppose the common domain of X is D. The notation here with the double arrow to the right means that every element in the truth set of P of X is in the truth set of Q of X, or equivalently, for all X, if P, then Q. If with the notation P of X with a double arrow, Q of X, means that P and Q have identical truth sets, or equivalently, for all X, P biconditionally implies Q. So let these be statements, these predicates be defined. Suppose the domain of n is the positive integers. Use the symbols to indicate the relationships among Q of n, R of n, and S of n. Well, one way to look at it is R of n is a subset of Q of n, so the right arrow would go from R of n to Q of n. R of n and S of n are the same, so they can have the bidirectional arrow. So n is a factor of 4, and n is would be pointing to the n is a factor of 8. And R of n and S of n are the same, so they can have the bidirectional arrow. And since these two are equivalent, you can substitute this for this, and from number 1, and have it the right pointing arrow pointing to n is a factor of 8. Now, Tarski's world. Computer program developed by some information scientists to help teach principles of logic. The program for Tarski's world provides pictures of blocks of various sizes, shapes, and colors, which are located on a grid. This is an example. I'm going to ask you guys to go through this on your own from the slides after I upload them this evening. But because it requires going back and forth a bit to reference this one's figure here. But the configuration can be described using logical operators, such as triangle, X meaning X is a triangle, blue Y meaning Y is blue, right of X and XY meaning X is right of Y, but possibly on a different row. Individual objects can be given names such as A, B, or C, and gives a few examples of finding the truth or falsity of each of the following statements. given the figure on the previous slide. For all t, triangle T is blue. Or if T is a triangle, T is blue. For all x, if x is blue, then x is a triangle. There exists a y such that y is a square and d is to the right of y, and so on. So, and the answer is given on the last slide of the deck. So, on your own, go back and forth, work out the logic and all that sort of stuff. Heck, you might be able to find on a app store somewhere, Tarski's World has a program. But play around with it, work out the different logic problems on that. Move on to section 2. And it's not going to cooperate again. Yeah. Come on. Okay. Predicates and quantified statements, part 2. More of the same. Negations of quantified statements. Just like the logical statements that we studied in chapter 2, quantified statements can be negated as well. Negation of the form given is logically equivalent to a statement of the form there exists an element in D such that Q is not true. Q of X is not true. So the negation of a universal statement is a existential statement, where you invert the predicate. So the negation of a universal statement is logically equivalent to an existential statement. When we speak of logical equivalence for quantified statements, we mean that the statements always have identical truth values no matter what predicates are substituted for the predicate symbols, and no matter what sets are used for the domains of the predicate variable. All right, the negation of the form of a existential statement is logically equivalent to a universal statement where the predicate is inverted. So for all x in D, not Q of X, Q is not true for X. Thus, the negation of an existential statement is logically equivalent to a universal statement. All right, formal negations of the following statements. For all primes P is odd, which is false. There exists and the negation would be there exists a prime P such that P is even, which is true because 2 is a prime number and it's even. E is a triangle for each triangle T such that there exists a triangle T such that the sum of the angles of T equals 200. Now for all triangles T, the sum of the angles does not equal 200, which is true. By applying the rule for negation of a universal statement, you can see the answer is for there exists a prime p such that p is not odd. I'm sorry? And for all triangles T, the sum of angles of T does not equal 200 degrees. You need to exercise special care to avoid mistakes when writing negations of statements that are given informally. One way to avoid errors is to rewrite the statement formally and then take the negation using the formal rule. And then the implication would be here to translate it back into an informal form after formally taking the negation. Rewrite the following statements formally, then write formal and informal negations. No politicians are honest. The negation would be that would be the formal form of the statement, yeah. What about the negation?
I said for every politician, he is not honest.
Oh yeah, that was no, that would be restating the statement. The negation of it would be there exists a politician who is honest, right? The number 1357 is not divisible by any integer between 1 and 37. What would the negation be?
There is an integer n between 1 and 37, such that 1357.
That would be a good negation of it. Yeah. A formal negation. There exists an integer n between 1 and 37, such that 1357 is divisible by n. Informally, the number 1357 is divisible by some integer between 1 and 37. Negation of universal conditional statements. Now, negations of universal conditional statements are of special importance in mathematics. The form of such negations can be derived from facts that we have already established. So, by the negation of a universal quantifier, you get this. But if you look at the negation of a conditional from chapter 2, you get this form. So you can say the negation of the universal conditional statement is for there exists an x such that p of x and not q of x. So formal negation for a statement and an informal negation for a statement. there exists a person P such that P is blonde and P does not have blue eyes. For B, the negation would be if a computer program has more than, there exists a computer program that has more than 100,000 lines and does not contain a bug. You get rid of the if and substitute it with the and statement. So, yeah. And the relation between the universal quantifier, the existential quantifier, and or. Negation of a for all statement is a there is statement, there exists statement, and negation of a there exists statement is a for all statement. These are analogous to De Morgan's law, which state the negation of an and statement is an or statement, and that the negation of an or statement is an and statement. In a sense, universal statements are generalizations of and statements, and existential statements are generalizations of or statements. If Q of X is a predicate and the domain of X, domain D of X is the set X1, X2, yada, yada, yada to Xn, then this statement is the equivalent to Q and Q of X1 and Q of X2 and so on and so forth to Q of Xn. So for example, if D is 0 and 1, for all X, and Q of X is X squared, X times X is X, for all X in D, Q of X is the same as Q of 0 and Q of 1. Likewise, there exists an X that's an element of D such that Q of X is the equivalent to Q of X1 or Q of X2 or yada, 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 Q or Q of Xn. So if Q of X is now equal to, or is the equivalent to X plus X equals X, and D is still the binary digits, then it can be written with the symbols Q of 0 and or Q of 1, which is true because 0 plus 0 is equal to 0, even though 1 plus 1 does not equal 1. So the overall statement is true. Vacuous truth of universal statements. Best demonstrated with a example. Suppose a bowl sits on a table and next to the bowl is a pile of 5 blue and 5 gray balls, any of which may be placed in the bowl. The 3 blue balls and 1 gray ball are placed in the bowl as shown in the figure. The statement all balls in the bowl are blue would be false since one of the balls in the bowl is gray. Now suppose that there are no balls placed in the bowl. All right. All the balls in the bowl are blue. Is this statement true or false? If the statement is false if and only if its negation is true. And its negation is there exists a ball in the bowl that is not blue. But the only way for this negation to be true is for there to be a non-blue bowl in the ball. And there's not. So the negation is false, and so the statement is true by default. So, like the vacuously true conditional statements of chapter 2, it is vacuously true if and only if P is false for every X in D. If P is false all the time. Variants of universal conditional statements. A conditional statement has a contrapositive, a converse, and an inverse. Covered this in chapter 2. The definition of these terms can be extended to universal conditional statements. Contrapositive is the inverse of the two predicates and flip them around from P then Q to not Q then not P. The converse is just flipping the two predicates around, so it's if Q then P. And the inverse is the inverse of the predicates without flipping them. So it would be if not P, then not Q. Informal, contrapositive, converse, and inverse of the following statement. For a real number, if a real number is greater than 2, then its square is greater than 4. The contrapositive would be flip the phrases and invert them. So it would be if a number is a square greater or less than 4, less than or equal to 4, then the original number is less than or equal to 2.
The square of a number is the original.
Because less than or equal to 2 and less than or equal to 4 is the inverse of greater than. So the inverse of the statement, if a number is less than or equal to 2, then its square is less than or equal to 4. If a square of a real number is less than or equal to 4, then the number is less than or equal to 2. Which isn't necessarily true. If the squares less than 4, yeah, I guess it would be true. But anyway, getting into arithmetic in my head, it hurts. Let's see here, the inverse. If a real number is less than or equal to 2, then the square of the number is less than or equal to 4. That one is not true, because -3 is less than 2, but its square is greater than 4. So Necessary and sufficient conditions, and only if. These are just different ways of saying this, some of the same things. If Rx is a sufficient condition for Sx, that means if R, then X. If R is a necessary condition for S, then if not, that means if not R, then not S. Or equivalently, because of the contrapositive equivalence, if S, then R. R of X only if S of X means that means if not X, not S, then not R. Or equivalently, again, because of contrapositive equivalence, if R, then S. So these two are basically the same thing. The sufficient condition and only if, because they evaluate down to if R, then S. Rewrite each of the following as a universal conditional statement, quantified either explicitly or implicitly. If X is a square, then X is a rectangle. All squares are rectangles. If you're the President of the United States, you're at least, if a person is the President of the United States, then they're at least 35 years old. Yeah, if you flip them around, the second part is given first in the if statement. So if a figure is a square, then it is a rectangle. If X is younger than 35, then X cannot be President of the United States. Or the contrapositive of that, if X is President of the United States, then X is at least 35 years old. A product of two numbers is 0 only if one of the numbers is 0. So by if it is not the case that one of two numbers is 0, then the product of the numbers is not 0. But the contrapositive of that is, if neither of the two numbers is 0, then the product of the numbers is not 0. Huh? And yeah, I just did the contrapositive. And that wraps up the slides for the day. Try to cover 2 sections a day. Any questions? Requests for clarity?